So as always happens, we're of course way behind. So Tom's demo is actually quite important. So what I will do is I will.
I'll try to do it quick. So
Well, I will cut mine. This overview short. So oops, it doesn't look too good.
Whoa.
Let me just see if I can. Oh, okay, it recovered. So I will just start with my presentation and probably cut it somewhat short. These slides will be online, and if you want to read more about it or talk with me about some of the details, then I'd be happy to do that this afternoon or anytime. So this is sort of a little bit more it's an autopilot. Interesting. Didn't know it can do autopilot. All right, let's see if it starts again. So if you wanted to discuss some of these more mathematical concepts in more detail, we can do that definitely this afternoon, over the next couple days, or whenever you want. So the goal of this, so this is a little bit more theoretical. So for those of you who are not theoretically inclined so much, it's not that important really for using MCell, but it's mostly to show you kind of what the foundations are of some of the algorithms that we use, some of the approximations that we of course make to do these kinds of simulations, so that you can kind of see what's really going on under the hood a little bit. And it's by no means detailed enough to tell the whole story, and there's 2 publications that are listed here that might be good starting points for those of you who really want to learn a little bit more about what's going on under the hood. So I'll really just touch on some of the basic things that are happening. So again, these slides will be online, and you're welcome to take a look at these papers for more detail. So I will take the next 20 minutes to do that, and then I'll hand it over to Tom to show you a little bit about the kinds of things you can actually do with CellBlender. And again, if there's questions, please ask. So the kind of key observation, that's of course a pretty severe approximation, is that to a large degree, cells consist of lots of biomolecules that we're interested in, and a lot of other stuff that we may be not necessarily interested in specifically, like water molecules. There's a lot of water molecules in living tissue, and this is just a box of water molecules. It's fairly small. I think it's 30 angstroms by 30 angstroms, if I'm not mistaken, maybe 900 water molecules, but it just shows you how really densely packed the system is. And so one way, and so the relevant timescales here, and it's always a little good to think about these a little bit. So the relevant timescales at the molecular scale are perhaps angstroms, 10 to the minus 10 meters, and timescales are on the order of femtoseconds. And the timescale really comes from the bond vibrations of your biomolecules. So the fastest vibrating bonds take about 10 femtoseconds. So these are CH bonds, typically some of the fastest bonds. So they vibrate on a time scale of about 10 femtoseconds, plus minus. So to really simulate that, to sample these vibrations, you have to have a time step of less than that. Typically it's a femtosecond. And so the simulation approach that a lot of people do to run these simulations, and one approach to do this would be to use just classical Newtonian equations of motions, very simple in a way, is a methodology called molecular dynamics. And basically what people do is they solve this equation of motion that describes the time evolution of your location of particles in the presence of some potential that, in the case of molecular dynamics, is empirically defined based on experience. It actually works pretty well. It works surprisingly well given the simplicity of these simulations. The problem with molecular dynamics is, from my point of view and from many people's point of view, is that if you really take into account all the atoms in your system, you end up with a lot of atoms very quickly. And so you have huge systems, and a typical cell has trillions of water molecules. So there's clearly no way you could even, at least at this point, dream about simulating a cell at an atomistic scale. So people have managed to simulate things like whole viruses, which have tens of millions of atoms. So that's been possible. That's possible right now. The key problem with these simulations is the time scale. And the problem is that the time step of these simulations is femtoseconds. And so typical molecular dynamics simulations cannot reach much more than a couple hundred nanoseconds, maybe a microsecond. And so that's really the key limitation. All the important biological stuff happens in the millisecond time scale, typically longer. Many things take seconds. So if you can only simulate for 100 nanoseconds or microsecond, that's quite limiting. That's really the main limitation, I think, that this field has. And it's a big limitation, and you cannot solve it by throwing larger supercomputers at it. So you can simulate bigger systems, but you can't simulate longer. And so this is sort of this almost state-of-the-art in simulations of biomolecular systems are these MD simulations. Actually, PSC has a supercomputer called Anton, which was specifically designed to run MD simulations. So it's a special purpose machine that has chips that run MD in hardware. So this machine can do nothing else but run MD. It was designed by a company in New York, D-Show Research, that has spent a lot of money on designing this machine, and it runs about 100 times faster than the best machines we have on the planet. So it's very fast, but it still can only reach hundreds of microseconds, maybe a millisecond. So it's very fast for MD, but it's still very slow for the kinds of cell-level processes we're typically interested in. So if I want to simulate one action potential, in my case, I want to be able to simulate for 3 milliseconds at least. Anything less is not really that, and so that's not possible with these. So basically, that's the challenge. And so one way, I'm sorry for all the equations, I'm just going to talk about. So one way to really deal with this is to say, well, if you look at cell-level type systems, we're really not interested in all the degrees of freedoms. We really want to look at a subset of those. And so that could, for example, be the center of mass of our molecules. It could be some reaction coordinate, some process that we're interested in. And so we would say, well, if we do this, we just confine ourselves to a smaller number of degrees of freedom, perhaps just the few channels I'm interested in, and I take into account the rest of the system, most importantly the water molecules and all the solvent, sort of in a phenomenological way. Physicists would say integrate out these degrees of freedom, we come up with sort of renormalized type description. And the equation you can come up with is something like this. It just looks similar to the Newtonian type MD equation for this reduced set of degrees of freedom, but you get some additional terms. And these are actually the key terms here. So this term here is proportional to the velocity. This is a friction term that sort of embodies the viscosity of your system. So it basically embodies the presence of the water molecules without taking them into account explicitly. So molecules have some kind of resistance moving through the water molecules as they move through space. And then there's another term that represents the noise in the system. So you get a stochastic kind of component to it. And so this equation is actually quite famous. It's called the Langevin equation. It underlies a lot of different simulation approaches. This is just the one-dimensional example of that. And in our case, actually, when we want to simulate cell-level systems, we're typically in what's called a strong friction limit, namely that actually these frictional forces due to the viscosity of the system really are much larger than your inertial forces. And you can actually ignore this term. It's usually a very good approximation if you're interested in time intervals larger than a picosecond. So at that point, it becomes actually quite decent approximation in most cases, which is typically the case. So in MCell simulations, your time step is not going to be a femtosecond. It's typically a microsecond or tenth of a microsecond. And so in this case, you can actually simplify to this equation. And this is a stochastic differential equation that underlies a simulation approach that some of you may know or have heard of. It's called Brownian dynamics. So a lot of people actually use Brownian dynamics to simulate cell-level systems. There's a tool called LAMPS, which is quite widely used for stochastics, for Brownian dynamics simulations that more or less model Brownian motion of some particles in this imagined sea of water molecules that we don't treat explicitly. We just treat them as a friction, and they impart some noise so that particles move around randomly. And so this is maybe just a reminder to you, whenever you use any kind of simulation approach, it's always good once you use it more frequently, or it's a big part of your repertoire, to think about the kinds of approximations that go into these types of simulations. Any computational approach has some limitations. And so in particular, if you would want to use MCell to sample your problem at a time scale of 10 femtoseconds, it would probably not be a good thing to do. It's just not really designed to do that. So the assumption is basically that we're sampling things at a picosecond or larger, so we can ignore these fast fluctuations. Any questions about this? And so if there's actually no forces in your system, you can simplify this some more. And this is the standard Brownian dynamics type equation that's used quite a lot just to model Brownian dynamics. And a lot of simulation packages actually use this type of approach. And so what you basically do is here in this approach, you follow the time evolution of each molecule as a function of time as it moves through space in the presence of this friction term and in the presence of this random noise. With MCell, we take a different approach, and it's actually equivalent or corresponds to this equation. So instead of following every particle in space as a function of time, we ask a different question. We use a probabilistic approach. So we actually ask the question, given that a particle is right now here at this time, what's the probability for it to be here at a later time? So this is the kind of question we ask in MCell. So this is called a conditional probability density, where we basically ask just these questions. Given that a particle is here right now, what's its probability to be here, 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 here at a later point in time? And the evolution of the system is governed by this probability. So basically, what we are solving is this equation, and you can actually show mathematically that these are equivalent. So there's a way using, it's called Ito calculus, to equate the two. You can actually show that the system that you're sampling using this approach and this approach are equivalent, even though they have two different points of view. So here you really follow particles explicitly as a function of time. Here we're interested in the probabilities of particles being at a certain point in space at certain times, given that they were at point R0, T0 at a different time. And so this is actually what's known as the Einstein diffusion equation, or one incantation of it. So this is really, for the diffusion part of MCell, this is really what we're dealing with. So we're solving this equation, where we're sampling our system so that it actually is a solution to this diffusion equation. And for some of you may have heard this in sort of different contexts. So there's a famous German called Adolf Fick, who derived his first and second law where instead of the probabilities we have now concentrations, but it's the same concept, where we have here the diffusion equation, basically diffusion of stuff in space. Okay, so now from an MCell point of view, basically what we need to run our simulations is, at any given point of time, we have molecules in our simulation at different points in space. And so now we need to figure out a way where to put these molecules at the next time step. Right? So we have a certain configuration at time t0. Where are they going to be at time t plus delta t? So that's our question. And basically, we use this equation to compute where they will be in the future. So we basically, you can solve this equation. We assume radial symmetry, which is usually a good approximation in our case. And then you can actually solve this equation. It's a Gaussian distribution, as we know. And then from that, we can immediately actually come up with a equation for the probability for a particle to be displaced between distance r and r plus delta r in an arbitrary direction. So this really is the probability distribution that MCell uses to propagate particles during the simulation. And using this, we'll make sure that we actually follow this Einstein diffusion equation. So basically, we have a particle that sits here at time t0, and then we can use this probability to decide what's the probability that it'll move a distance r, that it'll be at a distance r between r and r plus dr at the next time step. And so just from a computational point of view, you can actually do this quite simply. So you use this probability. You can do the cumulative distribution function of this thing. And so basically, that goes from 0 to 1. And then the only task we have to do is you pick a random number between 0 and 1. And you can more or less read off using this equation how far you should go. So this is basically how you propagate particles so they sample this Brownian, this Einstein diffusion equation. And we assume it's a radially symmetric problem. So the direction of motion is just randomly picked 360, over your 4 pi angle. So this is basically what's happening every time step for each molecules. And of course, the distance you step depends on your diffusion coefficient. So the larger the diffusion coefficient, the larger the steps. And it also depends on your delta t, your time step in your simulation. But by the end of the day, what we do in MCell is that we have an algorithm that's numerically fairly efficient that more or less samples this Einstein diffusion equation for the probabilities of particle locations. So that's what we do. So in particular, the approximation here is that there's no external forces on these particles. They're just diffusing in this sea of water molecules that basically makes things viscous for them, so it's difficult to move, and that imparts sort of random noise on them. They bounce into them. And so if you run a simulation using MCell, using this approach, you'll see particles randomly bouncing around like you would expect if you would observe a Brownian particle under your microscope. It would look just like that. Does that make sense? I know it's a lot of math. And so maybe as the last item, I want to briefly tell you, so this basically covers the diffusion aspect. So this is how we propagate particles as a function of time in MCell. And so everything in MCell is probabilistic. Any event is triggered based on the probability for that event to happen. And so the last thing I want to talk about briefly are the simplest case for reactions that can happen, which are unimolecular reactions. So basically, we have some molecule in state S0 that has reaction rate constants to go to state S1, S2, and there might be many others. So particle basically going to transition into one of these states. So that's basically the simplest thing that can happen. And what we need to know is what's the probability for that to happen. So the user specifies the different states and the k values. So these come, you put these into your MDL file. You say k is 1 to the power of -5 or whatever. And so we have to, for our MCell simulation, has to figure out what's the probability for these reactions to happen given the values that you tell us, the k values in the states. And so the way to compute that is actually quite straightforward. So the probability for this transition to happen is basically the ratio of the population of all these states at time t. So how many particles ended up in state S1, S2, S3, divided by how much we had in the initial state. So that kind of tells you how much really happened with this transition, and you can rewrite it this way. So this is basically the definition of this probability. That's how it's defined. That's what it is. And the question is now, how can we actually compute it based on the k values? And we use the this relationship. So based on the rate equations, you can actually compute that the change in this population of the state is due to all the transitions that are mediated by these k values times the concentration in this initial state, right? And you can actually integrate that, and you find, and most people know that that's just an exponential. So it's a exponential distribution. So the probability is 1 minus e to all these k times t, right? And so the probabilities then for going into state 1 or state 2 or state 3 is this value times the corresponding k values over the sum over all k's. So that's how you can actually compute these probabilities. So basically, if you give us the k's in your MDL file, we can compute the probabilities for these transitions to happen using these formulas. And so now the kind of naive way to actually make these reaction happens is that at every time step, for each of these reactions, you compute the cumulative probabilities. Then you pick a random number between 0 and 1, and then you just say which one's going to happen or none. Right? So you do this every time step. And I say naive because it's fairly inefficient in the sense if a reaction is very rare to happen, you kind of sample it every time just to figure out that it actually didn't happen. So that's not a very efficient way to do it. And so the way we do it in MCell is actually that we assign lifetimes to molecules based on these reaction rates. So you can actually assign a molecule a lifetime, basically drawn from an exponential distribution based on these k values of when it actually should die or react or something should happen. And MCell has a concept of a scheduler. So a scheduler is a thing that basically schedules event at certain times. So what we do is we basically say, OK, what's the lifetime of this molecule based on the reactions that it can have? And then we put it in the scheduler at that time. Then we don't look at it ever again until that time actually hits. So basically, until that time, we're done with this unimolecular transition. So it's a much more effective way because you don't have to sample every time step and ask the question, will this happen or will it not happen, especially if these are rare events that don't happen a lot. So it's much more effective to say, well, this is a rare event, so it will happen way in the future. So I'm just going to make it happen in the future, and I don't worry about it until then.
And there's another effect of this, which is that what if it's extremely rapid event?
Yes.
That happens many, many, many times per time step. The scheduler will schedule it to happen later, during the same time step.
Yeah.
And then when it gets to that slot, the scheduler and sees that it's happening again, then it schedules it again. And then if that results in it being scheduled again granularity at which you're reporting how much stuff you have. And if you want to sample that more finely, you need a finer time step. But at least at the end of the time step, the state at that time, of including all the little microscopic things that happen during that time, have that sample.
Okay, I think, Tom, I'll turn it over to you. Again, there's a few more slides, but they'll take some time to go through. If you're interested, take a look. And if there's any questions, I'd be happy to talk about it. So what we'll do now is Tom will give you a sort of brief overview of what's possible using CellBlender and sort of this kind of tool chain we have developed. So his model is probably going to be the most complicated model that has been done with CellBlender. So that's not to mean that they all have to be that complicated. It's mostly to show you what you could do if you wanted to. And so this afternoon then we'll start off much simpler. You can design your own models, and we go step by step and build up more complex models. But I think it's a great example to show you how far you could push this if you want to, and if you have the data to really develop a model of this complexity. Right, Tom? Okay.